Hello everyone. Team 50 focuses on real versus fake image detection using transfer learning with ResNet and VGG-16. Today, advanced AI technologies has made it increasingly challenging to distinguish between real and fake images. Advancements in multimodal generative AI have enabled the creation of vast amounts of fake data, including images. While this has a positive uses like data set generation, it also raises concerns for identity fraud and spread of false information. Our project focuses on using transfer learning to enhance a basic CNN model, improving its ability to distinguish between real images and the images which are generated from AI. So our data set consists of two labels, real and fake. The real images are sourced from the Cipher 10 dataset, which is a widely used dataset which is also benchmark for image classification tasks. On the other hand, the fake images are generating using a combination of Cipher 10 input and a stable diffusion of 1.4, a technique for generating high quality images. We have a total of 1 lakh images for training with 50,000 images per class. For testing, we have 20,000 images with 10,000 images per class. All these images in our dataset are standardized to a dimension of 32 by 32 pixels, and this dataset composition allows us to train and test our model effectively for real versus fake image detection. So now my teammate Prathamesh will be explaining about baseline model. Over to you.
Thanks, Sumit. So for the baseline, we chose the convolutional neural net architecture where we had two convolutional neural layers of size 32 and 64, a 3 cross 3 kernel and a 2 cross 2 Boolean layer. The rest of the hyperparameters are mentioned on the slide. Next. So the performance for this model was 89.51% for training accuracy and 89.30% as the validation accuracy, and we could not improve upon this model. So we decided to use transfer learning for this project, which is this idea that you take a pre-trained model which has been trained on a generic data set and then you fine-tune it based on your use case. And we decided to use the ResNet 50 and the VGG-16 models, which Atharva will now explain.
Thank you, Prathamesh. So the first architecture that we used was the ResNet architecture, which stands for residual network. So for very deep neural networks, there's the vanishing gradient problem, and that is solved using the residual blocks, which contain skip connections. In our project, we use the ResNet 50 as the base model, and on top of that, we built a couple of layers, such as two dense layers and one final classification layer. ResNet is widely used in image classification tasks, and we used a pre-trained model which was trained on the ImageNet dataset. As we can see, so after training for around 18 to 20 epochs, the loss had dropped below zero point 0.1 and the accuracy had shot up to 99%. More about that later. The VGG-16 model was the other transfer learning model that we used. It has 16 layers, which includes 13 convolutional layers and 3 fully connected layers, that is dense layers. Just like ResNet, it was also pre-trained on the ImageNet dataset, and it is also used widely for image classification. On the right side, we can see this is our model architecture, which has the base network as VGG-16. And on top of that, just like the ResNet, we've added 2 dense layers and 1 final classification layer. So coming to the performance comparison, the baseline model had a training accuracy of 89.51%, whereas both ResNet and VGG crossed 99% accuracy. And in validation accuracy, VGG-16 slightly outperformed ResNet by 1%, but both were way ahead of the baseline model. So in conclusion, we've been able to show that transfer learning is a better method and more efficient than training your own custom CNN. Overall, we can crown VGG-16 as the winner in this case due to its higher validation accuracy. For future work, maybe we can try some hyperparameter tuning and maybe train on a bigger and better data set, as this data set had images that were only 32 by 32 pixels in size, which were low quality images. Maybe we can use better quality images in the future. Thank you.